Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, we're glad to have Shayan in the area and also giving a talk over here now. Again, he has some very, very exciting work on the traveling salesman problem, and he'll tell us about effective resistance reducing flows, spectrally thin trees, and ATSP.
Hello. This is a joint work with Nima, who is a PhD student at UC Berkeley. Thanks for inviting me here. I want to tell you about TSP. So basically, the first half of the talk would be more or less overview, some not that deep. I hope all of you understand. Then we may get more deep. I'll try to keep it simple for this talk, but then there will be a more details talk right after this. So so let's start. So I want to talk about asymmetric TSP. So we're given a set of cities and their pairwise distances, which is non-negative and satisfies the triangle inequality. The goal is to find the shortest tour that visits all cities exactly once. Okay? And we say that this is asymmetric if the cost function is not necessarily symmetric. Okay? The cost of going from here to UW may be different from the cost of going from UW to here because of the traffic or whatever. Right? So this is asymmetric TSP. Good. So there is a natural LP relaxation for this problem by Held and Karp in 72s. And you don't need to understand this LP. I'm not going to use it. I just put it for the sake of the talk. So it's the nice thing is that it's a basically simple LP. And for a very long time, people thought that this should be very useful and should give us a very good estimate of the value of the optimum tour. We should be able to use it to design algorithms. But on the other hand, we didn't know much about it for many years. It's also interesting to study the integrality gap of this LP, which is the ratio of the optimum, like sort of a worst case ratio of the optimum integral solution to the fractional solution. Okay? Okay, so let me just say one very briefly. Very briefly, this LP, what it says is that in the TSP tour, you have to leave each vertex. Like whenever you enter a vertex, you have to leave a vertex, and for every cut, you have to leave that cut at least once. Okay, that's what it says, but you don't need to understand. Okay, so here are some previous works for ATSP. As you see, there are quite a lot of works. There was a log n approximation by Fries, Galbietti, and Maffioli, and this has been improved. Some of the people in the audience have also improved it. So recently, like 5 years ago, sort of, this was improved to log n over log n. So finally, better than log n in the asymptotic way. This was a joint work we had with I had with Asadpour, Gomez, Madri, and Saberi. And also we know that if the graph is like planar or bounded genus, then the problem is really easy, like we can get a constant factor approximation. Okay? So the belief is that we should be able to do constant for every, in general. Now, what do we know for the integrality gap of the LP? We know that it is at least 2, okay, just number 2. One second, and it's at most log n over log n. It means that when you drop the directions, it's planar. Like, so basically you can, yeah, you can assume that you have a cost function only on pairs of vertices, and then for the rest of the pairs, the the cost is the shortest path metric. But another way of seeing it is that forget about the cost function, compute the LP solution. If the LP solution is planar, then this thing works. Okay? So for whatever cost function, if the LP is in planar, this works. You get constant. All right? So that's it. So here's the result I want to tell you about, that we show that for every cost function, the integrality gap is polylog log n. Okay, so from log n, basically, or log n over log n, we can get down to log n. So this is one of the instances of the problem that right now we know how to bound the integrality gap, but we still don't have an algorithm. We're thinking about it, but still we don't have. If you're also interested to know what's the exponent of the polylog log, it's about probably 10 or something. Okay, is this clear? Okay, so here's the outline of the rest of the talk. I start talking about thin spanning trees, and I'll tell you how they are related to asymmetric TSP. Then I'll tell you about spectrally thin spanning trees, and then I'll tell you what our approach, the algorithm, and something about the proof. Okay, so let's start with the thin spanning trees. Okay, so in this slide I'm going to define it, and then I'll tell you how it is related to ATSP. Okay, so what is a thin spanning tree? Suppose, for the sake of this slide, suppose we have a k-connected graph. So the graph is like now undirected, unweighted, just a simple graph. You can have parallel edges, but it's a simple graph. Okay, you have a kh connected graph, and you say a tree, a spanning tree, is thin, alpha thin with respect to g, if for every cut you have this. You have that the tree has a few edges in the cut with respect to g. Right? It has at most. Say again?
You should define people.
Yeah, I'll say that. So by k-connected, what I mean is that there are multiple ways you can see it. One way is that in every cut, the graph has at least k edges. Another way is that the graph has at least k over 2 edge disjoint spanning trees. This is kind of equivalent up to a factor of 2. Then another way of defining it is that for every pair of vertices, there is a max flow of value k from one to the other. So all of these are properties of kh connected graphs. Okay, so you have a kh connected graph. You say a spanning tree t is alpha thin with respect to g, if for every cut it has few edges in the cut. Okay, alpha fraction of the edges of the cut. So here is a simple example. If you have a complete graph and you take this Hamiltonian path, then I claim it's a 2 over n thin tree. And why is that the case? Look at every cut in the graph and the corresponding cut in the tree. Okay, note that the cuts are not necessarily this. Like I can, for example, choose every other vertex. Okay, so for every cut. Okay, now for every cut in the graph, if I have k vertices on one side and n minus k vertices on the other, then there are k times n minus k edges in the cut. But the tree has at most 2 k edges, because the degree of each vertex is 2. Okay, so you get 2 over n thinness. Make sense? Okay, so it's easy in the complete graph. In fact, for a complete graph, every bounded degree spanning tree is a thin tree. Is like a constant over n thin tree. Okay, so if you think it's a simple problem, you can try to find a 1 over k thin tree in a hypercube. Okay, it's a try to do it the rest of the talk. One other thing. Okay, so there are a couple of things which is interesting to note here. So one is that the tree is not something special here. You can ask for you can define this for any subgraph. Now the thing is, if you have a subgraph which is alpha thin, any subgraph of your subgraph is alpha thin. Okay, so in fact I can look at connected alpha thin connected, like spanning connected subgraphs. Okay, this is also interesting. Or I can look for alpha thin matchings, edge covers, any sort of things that any sort of sets of edges. Another thing is that this object is also closely related to cut spacifiers. So a cut spacifier of a graph is a subgraph that sort of approximates the size of the cuts. Now, the problem is, so this is, you can think of this object in a sense as a one-sided cut spacifier. Like if here we also have some like maybe alpha times 1 minus epsilon E of SS complement, then this would be exactly a cut spacifier because the tree would approximate the value of every cut within like 1 plus or minus epsilon factor. Here we don't have this, so it's like you can think of it as a one-sided cut spacifier. And for those of you who are familiar with the literature of the spacifiers, the reason that this is not an easy problem is that the tree must be unweighted. Okay? So if you're allowed to make the tree weighted, then the problem becomes very easy. Okay? If you make the tree weighted and then you, instead of the number of edges of a tree in the cut, you just add up the sum of the weight of the edges in the cut, then the problem becomes easy. Okay, is this clear? Good. Now let me tell you why I'm saying all this. Right? How is this related to ATSP? So here is something that we proved with Asad Poo, Gomez, Mantri, and Saberi that if for log n connected graphs, alpha is less than this, f of n over log n, you get order of fn approximation. Like, okay, if you can just prove that a tree exists, you get an order of fn approximation on the integrality gap. If you can find the tree, you get order of fn approximation for algorithm. Okay, so basically, again, something which is so again for this problem, something which is important that you need to assume that k is really small, like log n or even smaller. Okay, and this is the interesting regime of the problem. Okay, especially for log n, it's what we have for ATSP.
N over here is the size of the graph.
N is the size of the graph. Yes. Okay. Now let me tell you what do we know. So here are what we know, some conjectures and some results, like previous to our work. So this was a conjecture by Godin that he came up to this conjecture because of applications of this problem to nowhere zero flows. Okay, if you don't know it, you don't need to know it. So he conjectured that there is a number k, okay, maybe 2 to the 1,000, right? That any kh connected graph of any size, like n is arbitrarily large, has a 0.99 thin tree. Okay, so basically what you should think that this conjecture says even 1 minus epsilon, like 0.999 thin tree is something non-trivial. And we still don't know the answer to this conjecture. And so for the rest of the talk, whenever I say a thin tree without saying the alpha, I mean something of this kind, something less than 1. Okay? And the reason that this is interesting is that if you have this says that like, you can use this to say that log n connected graphs has log n to the minus epsilon thin trees. Okay, so you get better than log n approximation for ATSP. Whenever you want to go from thinness to ATSP, you need to multiply this by log n. So you get log n to the 1 minus epsilon for ATSP. Okay, so
It exists again. It's not for log n.
yeah, this doesn't directly imply that. You need to do something, but it implies. If you repeatedly apply the same thing, you'll get that. Okay, and here are some other results. So in the 2009 paper, we show that any log n connected graph has a 1 over log n thin tree. And this gives log n over log n approximation. In this work, we show that planar bounded genus graphs has 1 over k thin tree. And this last work, I'll say much more about it for the rest of the talk, says that if your graph is edge transitive, meaning that think of it as a symmetric graph, okay, like a hypercube, okay, then it has 1 over k thin tree. Okay, so 1 over k is the optimal thing, right? If we can get 1 over k, like if we can get 1 over log n for log n connected, we would get constant, right? So okay, so I'll say more about this RAS result later. Okay. Any question here?
having thin tree implies LP has small it. Is that will you give an insight into that? That result.
Yeah. Basically, the proof is just a max flow min cut argument. Okay, so what you do is that you say if the tree exists, you use a sort of a max flow with a lower bound of 1 on the edges of a tree, and then you use the solution of the LP to show that this flow can be routed in the graph. Okay, so you put the lower bound of 1 on the edges of a tree, some upper bound on the rest of the edges using the LP, and then you say that you can like use the max flow min cut theorem and say that this flow can be routed. It's not that complicated. And when you know the connection, it's not that complicated to prove. Okay, so what do we do here? Here is our result. Basically, it says that we say that for every log n connected graph, every log n connected graph has a polylog log n over log n thin tree. Okay. In fact, like more generally, we show any k connected graph, as long as k is more than log n, has a polylog log k over log k thin tree.
Is there an example of a k connected tree without the 1 over k?
No. I mean, yeah, for all we know, it can be, yeah, every k connected graph can have a 1 over k thin.
What's some example by Yal that you get?
It would be very interesting if.
But maybe it was just for
Yeah, uniform spanning doesn't work. Okay, so is this clear?
But like just a constant, but that's only a constant.
Yeah, 2 over k, yeah, probably right, but not more than 2.
So it's still possible that you have constant over k.
Yeah. Okay, so is this clear? So I want to tell you, so for the rest of the talk, I'm only going to tell you about thin trees. I'm not going to tell you about TSP. Okay, forget about TSP. Okay, so it's basically a graph theoretic question, and I just want to tell you about that. Actually, if you ask a computer about a thin tree, here are the 2 answers I found. I think the right one is the Google answer, the left one is the Bing's answer, and you can. Okay. Anyhow, so let's think about thin trees. So okay, does who here knows about Laplacians of graphs? Like I've seen. So okay. So this is like a very fast slide about Laplacians. I need to say this then to define a generalization of thin trees. Okay, so bear with me for one minute. So the Laplacian of a graph is sort of, you can think of it as a normalization of the adjacency matrix. This is a Laplacian. Basically, the Laplacian is the degree matrix minus the adjacency matrix. So this is a Laplacian of this graph. On the diagonal, you have the degrees. Off diagonals, you have -1 if there is an edge from I to j. Okay, and then okay, you can write Laplacian this way. If you write chi uv to be like 1 minus 1 for the edge uv, then the Laplacian is chi e transpose for all the edges. Some of this, and then there is a natural quadratic form you can assign to Laplacian. It says the following: for every graph, the Laplacian like y transpose Ly for some vector y, you can write it this way. It's equal to summation of yu minus yv squared over all edges. Okay, so these are some basic facts about Laplacians. If anybody want more details, I'll be happy to say. Okay, so I'm going to use this quadratic form in the next slide. Okay. So what do I want to do? So the thing is that okay, thin trees are nice. Why? Because they're sort of very graph theoretic. Like you don't need to worry about direction of the edges, the cost of the edges, nothing. Right? Just you have a graph, you want to do something with it, right? So they're nice in this sense, but they are not nice in another sense, which is that if I give you a graph and a tree, it's not easy to see, to prove that a tree is thin with respect to the graph. Okay? So if you think about it, it's basically an instance of a sparse cut problem. So it's something you can approximate it, but it's not an easy object to deal with. Okay? So because of that, we want to work with a generalization of thinness, which is called spectral thinness. Okay? So what is this? Again, we have a k-connected graph, G. Now we say tree T is alpha spectrally thin with respect to G if this is true. If the Laplacian of T is at most alpha times the Laplacian of G. And this is in the PSD sense, in the sense that this matrix minus this matrix is positive semi-definite. Okay? And the Laplacian of a tree is just the summation of chi transpose on the edges of the tree. Okay, so it's what it should be. Okay, so why are we defining this? There are two reasons. One is that it's a generalization of thinness. So if a tree is alpha spectrally thin, it's also alpha combinatorially thin. Why? The proof is really easy. Look at any set of the vertices, and let's say this 1s is the indicator vector of the set S. Then by that, I can write this for every set S. 1s transpose L of T 1s is less than 1s alpha times 1s transpose L of G 1s. And then the left side, so this object is exactly the number of edges of the tree in the cut SS complement. This is the number of edges of the graph in the cut SS complement. Just remember, this is the quadratic form. So this is basically summation of u and v, which are neighbors, 1s of u minus 1s of v squared. And then, so if u and v are in the different sides of a cut, this is 1. Okay, so this is exactly the quadratic form, and then this is true. Okay, so again, spectral thinness implies combinatorial thinness. So it's a better quantity. It's a stronger quantity. The other property is that it's testable in polynomial time. Okay, so basically all you need to do is to compute the maximum eigenvalue of this object. Like if I multiply LG minus 1/2 to both sides of this, in the right I'm going to get I, in the left I'm going to get this object. So the max eigenvalue of this is exactly the spectral thinness. Okay, so for every tree, it's just the eigenvalue problem. I can compute it, really understand it analytically. It's a very good object. Okay?
Which way are you computing the minus half?
Right. So I should say one thing is that L of G is not necessarily is always singular. It has the first eigenvalue is 0. But by this, I mean that forget about the first eigenvalue. Then yeah, just inverse all of the other eigenvalues and take the square root of them. Take the sum. So it's basically if you forget about the first eigenvalue, an eigenvector projecting the rest of the linear space, you can do the square root in that. But okay, you don't need to get into this in the talk. Okay? Just assume that it is non-singular. Okay, so now we have this. Okay, so it seems good. We have an object which is we can really good understand it. Now let's see how we can use it and if there are some barriers. The thing is that there are some barriers with this new definition. There are graphs with no spectrally thin tree. Okay, so there are graphs that has combinatorially thin trees but no spectrally thin trees. Okay, so what do I want to do in this slide? I want to give you a necessary condition for the spectral thinness of a tree. Okay, and then I want to use that to show that there are graphs with no spectrally thin tree. Okay, so here is a lemma. It says that if you have a graph, you have a tree, the spectral thinness of a tree is at least this object, the max effective resistance of the edges of the tree. Okay. So what is effective resistance? Effective resistance of an edge UV, you can think of it as a leverage score of the Laplacian matrix if you're familiar with leverage scores. If you're not, it's just this object. It's just chi UV LG minus 1 chi UV. Okay, and remember that chi uv is this 1u minus 1v, like the vector of 1 minus 1 on the endpoints of the edge. Okay, so the claim is that the maximum of this is a lower bound on the thinness. So let me prove it. It's just very simple, just 2 lines. So here's the proof. Okay, so suppose you have a tree which is alpha thin, alpha spectrally thin. This means that L of t is less than alpha times L of g. Okay, that I know. Now, on the other hand, for every edge in the tree, this is true. Chi transpose is less than L of t because like because L of t is summation of chi transpose over the edges of the tree, and these objects are all positive semi-definite, so just one of them is less than the whole sum. Okay, so you have this first inequality. Now all you want to do is just multiply both sides on Lg to the minus 1/2. And then you get this. On this side you get alpha, on that side you get. Okay, I did a little bit more trick. So the thing is, you get alpha times I on this side, but the left side is rank 1. So if you do it correctly, you get exactly that. Okay, but essentially, yeah. Just multiply Lg to the minus 1/2 on both sides. This would become I or 1. Essentially, the left side would become the effective resistance. Okay, so again, what did we prove? We proved that the max effective resistance is a lower bound on alpha, on the spectral thinness. So now, what I want to do, I want to use this to show that there are graphs with no spectrally thin trees. Okay, so in other words, I want to show that there are graphs such that in every tree there is an edge with large effective resistance. Okay, so here is the graph. Okay, this is a graph where for every tree there is an edge with large effective resistance. So how do I prove that? I show that in this graph there is a cut where every edge in the cut has a large effective resistance. And because any tree must choose at least one edge of every cut, it says what I want to say. Right? So look at this graph. What is this graph? It's like k parallel paths at the bottom and at the top, and then k parallel edges in this cut. Like the distance of these edges is n over k. Like each pair of them is n over k. Okay. Now so these bottom edges have effective resistance 1 over k. That's like this just follows from this series parallel property of the effective resistance, like k parallel edges, the effective resistance 1 over k. Now, these vertical edges have effective resistance like 1 minus k squared over n. It's very close to 1. Think of k as log n, right, or something smaller. So it's very close to 1. And in fact, the reason is that, I mean, if you're familiar with effective resistance, it's closely related to effective resistance flows. So that the effective resistance of an edge is the energy of a flow, of a unit flow from one endpoint to the other. And for this edge, for example, if you want to send one unit of flow from this side to the other side, think of this as an electrical network. One way is to go directly, the other way is to go all the way here and then go up. And because it's so long, the energy of any path that goes all the way to the right is so high that you wouldn't do that. You just go straight up. Okay, is this fine? Okay. So again, what did we show? We show that there is a graph where in a cut every edge has a large effective resistance. That says that this graph doesn't have any spectrally thin tree. Now what do I want to do? I want to show you. So I showed you a necessary condition. I want to show you a sufficient condition for a spectral thinness. So this is a nice theorem that came up from this nice work of Marcus Spellman and Srivastava, who proved the Carrison-Singer conjecture. Follows from their work that in any graph has a spectrally thin tree with a spectral thinness this much, the max of effective resistance over all edges of the graph. Note that this is all edges. So if I have a graph where every edge has a small effective resistance, then my graph has a good spectral thin tree. Okay, so as an application, if you have an edge transitive graph, remember these are the symmetric graphs we were talking about, then because of this symmetry property, the effective resistance of any pair of edges is equal. So because if it is k regular, the effective resistance of every edge is 1 over k. So from this, you get 1 over k spectral thinness and combinatorial thinness. OK, sounds good? So let me summarize. Here is what I said so far. OK, so so I talked about 4 things. So what we have kh connectivity, and you want to go from this ideally to 1 over k combinatorial thinness. This is the thin tree conjecture that we're thinking about. Now, what are these bottom ones? These are the spectral versions. Something that we know is that if effective resistance of every edge is 1 over k, is at most 1 over k, then we can go from here to 1 over k spectral thinness, and from that to 1 over k combinatorial thinness. Okay? So if effective resistance of every edge is small, I'm done. But the bad news is that kh connectivity doesn't imply a small effective resistance. It's the other way around. Small effective resistance implies kh connectivity. Okay? So if this was the other way around, I could go all the way to the other. Okay? So what do I want to show next is our method. We're going to replace this with something much more complicated, but it's something that we can go from here to there, and from here to something similar to this, and then up. Okay? So, any question? Okay. So I want to. So next, I'm going to give you a sort of high-level overview of our approach. If you have time, then I'll dig more into it. Okay. Okay. So before saying the high-level overview, let me say one more thing. So I told you that in this Caddison-Singer, in this proof of MSS, if effective resistance of every edge is small, then we get a thin tree. But something even stronger is also true. If the average effective resistance of every cut is small, so there are edges with big effective resistance, but if you look at the average effective resistance of edges in each cut, that's small. Let's say 1 over 10, let's say. Then there's a 0.99 spectrally thin tree. Okay? So we don't need something that strong. Something much weaker is also true. Okay? This was something that we observed and follows from some generalization of MSS. Okay? So have this in mind. Now let me tell you how do we think about this problem. Okay? So here is the general idea. So what's the problem? The problem is that we are given a graph with large effective resistance. Okay? So we want to make it good. Okay? You want to sort of somehow reduce the effective resistances. Okay? So the general idea is that to try to symmetrize the graph in the L2 sense, reduce the effective resistances while preserving the structure of the cuts. So don't disturb the cuts. Cuts are essential objects for the thin tree. We don't want to ruin them. So preserve them, but try to maybe add some edges, remove some edges, do something to make the graph symmetric in the L2 sense, in the effective resistance. Okay? So before giving the more details, I want to give you one example. So remember this bad graph that we have. I want to tell you what can we do. Okay? This was sort of the start of our idea. What can we do for this graph? Okay? So here is one idea. Here's what we do with. So we're going to add these red edges. Okay? They all have weight k, and each of them goes from one endpoint of the vertical edges to an endpoint of another vertical edge, the next vertical edge. Okay? There are like k of them. And the thing is, when you add this, you can make sure that all of the black edges that I have now we'll have a small effective resistance. Because now when you want to route the flow from bottom to the top, instead of going through all this long path, you can just jump on this edge, jump up and jump back. And that saves you a lot. And the thing is, this edge is like, okay, it's like, it's much easier to go along this edge than these edges, because it's like, it has a very, the conductance of it is, the resistance is so small. So like the resistance of this edge is 1 over k. The conductance is k. So you can easily go here at the hop and then back, or so on and so forth, like 3 hops, 4 hops, off and back. Okay. So because of that, you can show that. Let's say, let me call this red edge graph D. Okay. So you can show that in this new graph, G plus D, the effective resistance of every edge is 1 over root k. Okay? So just by adding this red edges, I can decrease the effective resistances. And it's also not hard to see that the value of every cut is preserved. I've just boosted up the value of every cut by a factor of 2, no more than that, because you can use a flow to route these red edges. Okay? So is this clear? So now in this graph, every black edge has a small effective resistance, and I can hope to do something interesting. The red edges may have big effective resistance, but the black edges have a small effective resistance. Okay? So the general idea is to do something similar. Okay? So here is the general idea. We want to find a graph D, okay, such that the effective resistance of every edge of the original graph, every black edge, with respect to D plus G is small, 1 over 10 or 1 over k, something small. Okay? And such that D is not much larger than G in the cut sense. So the value of every cut in D is less than the value of that cut in G. So by this notation that I'm going to use the rest of the talk, I mean that the value of every cut in the left, for the left matrix, is less than the value of that cut for the right matrix, or this 1s transpose L of D 1s is less than 1s transpose L of G 1s. Okay? So it has two properties. It reduces the effective resistances. It preserves the value of the cuts. Now let's see what's going to happen. So if this is true, if I add D to G, then I can make sure that the effective resistance of every black edge, every edge of G is good, is 1 over 10, or it depends on the factor that I have at the top. Okay? Something small. Okay? So the effective resistance of every edge of G is small. Now, because D has few edges with respect to G in every cut, this brings down the average effective resistance of every cut. So although the edges of D may have big effective resistance, because they are not so few, they're not so large in every cut, the average effective resistance in every cut is small. So I can say G plus D has a spectrally thin tree. And when I have a spectrally thin tree for G plus D, this would be combinatorially thin with respect to G. Why? Again, because D is small with respect to G in every cut. So just losing a factor of 2, this would be, if I have 1/10 spectrally thin tree for this guy, I would get 1/5 spectrally thin tree for G. Sorry, combinatorially thin for G.
But it might have edges from D.
Okay, right. So I want to find, yeah, but it may not happen from, okay, so I can apply that to the small effective resistance edges. I can apply the Caddison-Singer, like the MSS proof to the small effective resistance. Okay? So basically what this helps me to do is that it allows me to bypass this spectral thinness barrier. That there are graphs with big effective resistance. I can add something to decrease the effective resistances and then use this machinery that we have. Okay? So this feels so good. It's like a general idea. Like basically, all you need to do is to show that this matrix D exists for every graph, right? And if you think about it, this is in fact a convex optimization problem. You can write I'll say later if you have time, but you can write a convex program that gives you the best D's. Like it feels so good, right? And so when we were at this point, we were like thinking probably it takes like no more than a month, right? That we should be done. And this was last Christmas that we were here. And yeah, the thing is, it doesn't work this way. Okay? The thing is, there are graphs with no good D, Okay, so here is a bad graph. Okay, so there are k parallel paths at the bottom, and then these other paths that jump, like this first path jump like 2 hops, then you jump 4 hops, and so on and so forth. So there are log n levels of paths. And the thing is, although these first level edges all have a small effective resistance edges, these other guys have big effective resistance. So for every d that you add to this graph, there is no way to decrease the effective resistance of these long edges. Okay? So I'm not going to tell you the proof of this now. Probably in the next talk, I'll tell you about it. Okay, so this doesn't work. But the good news is that something a little bit weaker works. So remember here, I wanted to decrease the max effective resistance of all edges of G. I want to find a D to decrease the max effective resistance of all edges of G. And here, this graph, what this graph shows is that you cannot do for all edges. But maybe you can do for some of the edges. And that's what we do. So here is the overview of the proof. Okay? So this big object, I'll parse it for you. But this big object is something that we replaced with what we had before. Before it was that every edge of G has effective resistance 1 over k. Okay? We replace it with this object. Okay? So what is this object? It says the following. There is a matrix D, which is like, okay, so first of all, D is not a graph. It's a matrix. But you can think of it as a graph. It doesn't matter for our application. So there is a graph D or a matrix D, whatever, and a set F of edges, okay, such that F is k connected, or omega k over 10 connected, and the max effective resistance over F with respect to D is small. Again, here it's not important to have D plus G or D. They're the same. Okay? So we relax in the sense, so relax sort of in two senses. In one sense, we're not looking for a graph. We look for a matrix, but that's not something that much difficult. The main thing is that instead of bringing down the effective resistance of every edge, we bring down the effective resistance of a subset of edges that induce the k-connected subgraph of our graph. Okay? So note that the graph F that we get may have, like, there could be cuts of the original graph with like n edges, but in F I have only k edges. So F is not in a sense related to the original graph. It's k-connected, but it may have much fewer edges in some cuts, or equal to the graph in some other cuts. Okay, so this okay. So the D is not a graph, I told you. Now, the bad thing here is exactly like one other problem that we face when we prove this is that this F, as I said, is very sparse with respect to the graph. Okay? Now, because of that, from this, we cannot show that the average effective resistance in every cut is small. If F was not sparse, if F has half of the edges of every cut, then the average effective resistance in every cut would be good, and we could use Carrison's, like this MSS proof. But unfortunately, F can be very sparse in some cuts. It could have much fewer edges. So because of that, we have to sort of extend this MSS results and prove that even with this weaker condition, D plus G has a 1 over k spectrally thin tree. And this tilde here means polylog. There's a polylog k hidden here. So there's a polylog k here. And note that k must be log n for this to be true. Okay, and then from here to there, it's obvious, right? Any spectrally thin tree of this guy would be combinatorially thin with respect to G because D is less than L of G.
And if D is not a graph, what does it mean, like, for a thin tree to be a tree? So what kind of edges it may have? Is it?
Say it again?
So in that bottom right
Bottom right.
angle, so D plus G has a spectrally thin tree. So in what sense?
Yeah, I mean the
explain
edges
what
of
it
G.
means to be spectrally thin, but in what sense is it a tree?
No. The tree is only from G. So I can choose some edges of G such that the tree that I get is spectrally thin, but not with respect to L of G at the right, with respect to D plus L of G, this other matrix.
It's a tree in G itself.
It's a tree in G itself, yes. Okay, so what I want to do, I want to tell you more about this, maybe in the next 10 minutes. In the next talk, I'm going to also tell you about the bottom direction, this one. Okay. Now, before that, I want to tell you something weaker. So note that, okay, from here, I can go to the bottom, then to the right, and to the top. Now, from here, I can also go to there, right? Because basically, if you have 1 over k thin tree, the graph is k connected. So you can go, like these all 4 are equivalent, right? So what I want to tell you about is how to go, like in the next slide, is how to go from here to there. Like this is something much easier to prove than this thing. Okay, it's just one slide proof. I want to tell you how I can go from here to there. And this was our motivation for coming up with this box. Right? It's like it's not a priori clear why something like this should be true. So the thing is, it's very easy to prove this, assuming the strong thin tree conjecture. And then you may hope that with something weaker assumption, this thing could also be true. Okay, so here is what I want to show again. I want to assume that every k connected graph has a 1 over k thin tree. I want to show that there is a subset F that is root k connected and a matrix D such that this is true. The effective resistance of every edge with respect to D is 1 over root k. Okay? So again, if every k connected graph has a 1 over k thin tree, there is a set F that is root k connected and a matrix D less than L of G in the cut sense such that the effective resistance of every edge with respect to D is small. This is weaker than what we prove, right? We prove 1 over k essentially. This is 1 over root k, right? But okay, it's interesting. Okay, so but the proof is very easy. Okay, so the thing is that if every k connected graph has a 1 over k thin tree, it must have a bunch of thin trees. Because if you have a k connected graph, you have a like 1 over k thin tree. If you extract it, the remaining graph is still k connected, maybe k minus 10 connected. So you can find another thin tree and then extract it and so on and so forth. So you can keep doing on this, find root k disjoint 1 over k thin trees. Okay? Maybe 2 over k trees, but something like that. Okay? So let's call these trees T1 up to T root k. Okay? So maybe this is the graph, this is the first thin tree, this is the second thin tree, so on. Now, I'm going to let F to be the union of these trees that I found, and let D be the following. So what is D? D is the, basically for every edge that I've chosen, I want to add an edge to D with weight root k. So D is root k times sum of the Laplacian of the trees that I chose. So here I add all of these red edges parallel to every edge that I've chosen, and the weight of every red edge is root k. Okay. Now the thing is, you can see that D is less than G in the cut sense because I have root k tree. Each of them is 1 over k thin. So their sum is 1 over root k thin. When you multiply by root k, it is less than G. Okay. So it's easy that this D is less than L of G in the cut sense. The other property is that the effective resistance of every edge of D, every edge of F with respect to D is small, because every edge of F is parallel with the edge of weight root k. So the effective resistance is 1 over root k only. Okay, so I mean, it's very easy, right? Just that if you have thin tree conjecture, the easiest way to find the D is to just choose many thin trees, add parallel edges to the trees that you have chosen with some big weight root k or whatever. Then the edges of the tree would be the set F that you're looking for. Okay, so I've shown you in this direction. Now, let me tell you in 5 minutes, like 5 to 10 minutes, a little bit about this. Okay. So I don't want to tell you exactly this. This is complicated. I want to tell you something weaker. Okay. I want to tell you about the following. Instead of So instead of finding a set F that is K connected, I want to give you a set F that has K over 2 edges incident to every vertex. Okay, so I just want to make sure that degree cuts are fine. Forget about every other cut. Okay, so I want to find a matrix D, a set F, such that instead of the following. So basically what I want to do is that I want to make sure that the average effective resistance, so this expectation is just the average effective resistance of edges adjacent to V for every V is small. If this is true, then you can simply set F to be the edges of a small effective resistance adjacent to every vertex V, and then F is good at least in the degree cuts. Sounds good? So just think that I want to think about degree cuts. And this itself is something highly non-trivial, because when you have this, when you add Caddison-Singer, like this MSS proof, it implies that there are 1 over K thin edge covers. There are subsets of edges with at least one edge incident to every vertex. This is already, we didn't know it. Okay, so sounds good? Yeah, this that exists you don't need. Sorry, forget about this. You just want to make sure that the average effective resistance of degree cuts are good, and then you let F to be the small effective resistance edge. Yeah, you don't need that exists. Okay, so now the claim is that this thing is exactly a convex program, and I will use its dual to analyze it. Okay, so it's the following convex program. So, okay, before saying it, note that I don't necessarily have to do this. Basically, all I have to do is to find a matrix D. That's good, but I don't know an easy way of doing it. Okay, that's why we look at the dual of convex program to show that the optimum D is good. Okay, so this is the primal of the convex program. It's easy. It says that the objective is the following. It's the minimum of the max of average effective resistance of degree cuts. So for all vertices, we look at the average effective resistance, we minimize the maximum. And then the constraint is that the matrix D that we get preserve the degree cuts. Okay, it's less than G in the degree cuts. So this is like, okay. So let me say two things. First of all, this is a convex function because matrix inverse is a convex, like you have this, these properties of matrix inverse. So effective resistance is a convex function. So this is a convex optimization problem. The second thing to note is that this also, although this is so small, it has like exponentially many constraints. You need to check this for every cut. Okay, so this convex program, you cannot run it in polynomial time, but there are variants of it that you can run in polynomial time. I'm not going to say it today, but yeah, there are variants of this, which is weaker in a sense, but you can run it in polynomial time. The other interesting thing to note is that if I drop this C here, okay, just look at this, then the optimum is obviously L of G. The best thing you can do is to just put D to be L of G. Basically, the whole thing is that this inequality lets you to choose a matrix that preserves the cuts and changes the structure of the graph. Changes the L2 structure of the graph. Okay, and the goal is that the claim is that for every K connected graph, the optimum of this is little o 1. Okay, so in fact it's 1 over K, but I'm not going to prove 1 over K today. Little o 1, let's say. Okay, so let me not go through the proof of this. we'll say it later. Let me just finish the talk. Sorry. Where is it? Okay. Okay. But yeah, but the overall idea would be to try to do all of that and then analyze it. So if you're interested, you can come to the next talk. So this was the main result. Again, we show that any log n connected graph has a polylog log n over log n thin tree. And that says that integrality gap of LP is polylog log n. The main idea was to show that basically to try to symmetrize the L2 structure of the graph while preserving its L1 structure, its cut structure. And there are lots of tools that we've used that I didn't have time to tell you about it. Like we use this method of interlacing polynomials with real estate polynomials. I'll tell you about the next talk. There are some graph partitioning tools, high dimensional geometry that I probably will tell you in the next talk. Okay. And here are some open problems. One thing that we're thinking about is that if the proof of these guys, Marcus, Pillman, Shrivastava, can be made algorithmic, and we now have a real interesting application, I think, in approximation algorithms. We're thinking about it, so it would be interesting. The other thing is that if we can prove C over K thin trees, constant over K thin trees, that would give constant factor approximation. We expect that our methods can do this, but we still cannot prove it. So we'll see. It's also interesting to see other implications of this. So the thing is, this kind of SDPs that we have is related to the Esparza-Scott SDP, and you can get many results out of this. You can, for example, get bounded degree spanning trees out of this kind of techniques. Yeah, it's interesting to see if there are some other new implications of this kind of techniques. All right.
Questions, comments? So I had a comment actually. So it was somewhat weird because from you said that if you assume the thin tree conjecture with the constant. With the constant, not one constant over k, then it implies only log n to the 1 minus epsilon approximation.
Yeah, as far as I know.
Okay, but now you've proven a weaker result because you say that one is like it's not clear whether it's weaker or something, but it's slightly different in the sense that we still don't know whether you can get a thin tree, which is just takes a constant fraction.
No, if you
pick like for ATSP, you prove a stronger. That implies a stronger result.
No, so the thing is that the assumption that I have is that you just prove that for some k, just for 1k, there is a 0.99 thin tree. If you prove that for every k there is a 1 over k, of course, it gives constant factor. Okay? You don't even need to do that. You just need to say that for a log n connected graph, there is a constant over log n. Even that is enough.
This was a constant k, right? So
yeah, the problem is with the constant k. If you prove for a constant k, then the best I know is log n to the 1 minus epsilon. But if you do it for log n, k equals log n, then yeah, you get constant factor.
So the Marcus Pillman Shrivastava stuff sort of gives you two-sided approximation spectrally, but you seem to only kind of need one side of this. Is it possible that there's a weaker result that maybe is easier to make algorithmic? That is enough.
So yeah, one reason that they give a two-sided approximation is that they have a very strong assumption. Okay, that effective resistance of every edge is small. That's very strong. And if you read their proof, the reason that they give a two-sided approximation is just sort of a byproduct. So the main proof is a one-sided approximation, and then there is a simple trick that becomes two-sided. Okay, so in fact the reason that we had to extend it is that it's not two-sided. The main proof is essentially one-sided. So yeah, I'll tell you a little bit more in the next talk, but yeah, I don't know if there is another way of, yeah.
Okay, so
All right.
this can